Hello, I am YouTube's very own That CoCo Town guy. Welcome to Asm Adventures, the series where we discuss all various topics about 6809 assembly, in particular, the implementation of the basic interpreter in the CoCo ROMs. Today is Joystick Day. We're going to do a deep dive into how these puppies work. We will first talk about the basic interface and a weird quirk. We'll then dive into the successive approximation algorithm and some surprising hardware considerations when delivering analog joystick voltages to a running digital program. By the way, I was first introduced to the successive approximation algorithm by this video by Retrying Lab. He also goes into far more detail on the hardware than I possibly could. So if you'd like to explore further, I highly recommend it, and there is a link to it in the description. Now, I know what you're thinking. You're probably thinking, bro, that is one clickbaity title. Well, let it be known, here at CoCo Town, quality is job number one. And if for whatever reason you are not fully satisfied with the content of this video, you are entitled to a full refund. And that is a CoCo Town guarantee.
Not a guarantee. All claims are false. Watch at your own risk.
We're going to run this simple code. It will first print the value of the right joystick, X and Y axes at location 0 and 5, and then the left joystick's X and Y axes at 10 and 15, and then it will go back and repeat. You can ignore this, that's some weird artifact from Toolshed that I never quite figured out. I have it configured so that this is my right hand joystick and that is my left joystick. So we'll play with the right joystick, and up, down, right, left, up, down, and then my left joystick, left, right, up, down. Okay, fairly as expected. Now let's say I only care about the left joystick, so we'll just not do 20 and 30. What do you expect to happen? Okay, well, yeah, there's that. If I fiddle with my left joystick, nothing. That's odd. My right joystick? Nothing. Nothing works. Everything is broken. What? What if I were to do this? That really shouldn't change anything, right? Because all we're doing is we're getting the value of the x-axis of the right joystick, sticking it in A, and ignoring it. That will have no effect whatsoever on this. Why? Why?
That is so shocking. I'm very surprised.
I recently discovered this, or maybe rediscovered this, when I was going through Unraveled looking at the joystick routine. When the joystick function from BASIC is called, we end up here. We grab the function argument, we make sure that it's within range, and then we ask whether the argument is 0 because we get new data only if joystick 0. This conditional branch decides whether or not we're going to fall through to get joy. getJoy is what actually evaluates where the sticks are and then fills 4 memory locations with those values. If we're not being called with 0 as the parameter, we're not going to get anything. And then the next line actually goes through those 4 memory locations, figures out which one that we want, and returns that to basic. And those 4 memory locations start here at 15A. When I saw this, I had no memory of this limitation, and I was like, does the color basic manual actually tell you about this? Because this seems crazy. In fact, yes it does, and the manual walks you through the exact same thing that I just walked through. And it explicitly says, anytime you're having the computer read the coordinates of joystick 1, 2, or 3, you must first have it read joystick 0. I probably read this back in the day, but I have no memory of reading this. And in fact, you can get away with not knowing this most of the time, because most of the time you're writing software that deals with the right joystick, and maybe both, and rarely just the left one. So just a matter of routine, you probably are checking joystick of 0 first anyway, and this limitation just doesn't bite you. The reason they do this is presumably it's expected that you're going to be reading all the joysticks to do some kind of detection of game elements, and it's just faster to go into the ROM, read everything at once, fill out those 4 memory locations all at once, and then as you need them, it will just go into here and retrieve them rather than having to remeasure them every time. From here on out, we're going to take a deep dive into here, getJoy. So this is the routine that gets called if joystick 0 is what got called from basic. getJoy is responsible for returning a digital value, a digital reading off of the analog joystick. And that means we're going to start getting into the CoCo's analog to digital converter. Which brings me to the next shocking secret. The CoCo's analog to digital converter contains a digital to analog converter.
That is so shocking. I'm very surprised.
It's my birthday recently. For my birthday, I got a humidifier and a dehumidifier. Put them in the same room, let them fight it out.
Analog to digital converters and digital to analog converters are arch nemeses, but somehow they're in cahoots. How is this possible? All will become clear soon enough. getJoy is otherwise known as JOYIN, and it starts over here. At this point, B is going to represent which of the 4 axes we're going to be looking at. So that's either left, right, up, down for either the left joystick or the right joystick. That value is used in this routine, which selects the inputs on the analog multiplexer. If you watched my previous series on assembly language sound, you know what that means. That's the selector switch that decides, among other things, what sound to send out to the TV. So in that series, we were taking the DAC, which got its bits from here, and which sent its result to slot 0. If the selector switch is pointed at 0 and the master select switch is on, then that will allow the DAC to go out to the TV. But the selector switch can be used for a lot more than that. It also can decide which axis of which joystick goes out to the comparator on the positive end. And that's what this routine is doing for us right now. It's deciding which of these 4 axes we're going to try to read. But what's this comparator all about? We choose an axis from a joystick, we send it to the comparator, but why? What are we comparing it to? Well, if you're a hardware ignoramus like I am, you probably would have expected that an analog joystick would send its value to the software, and the software would say, thank you, now I know your value. But it is not like that. You literally have to play a game of 20 questions, asking the joystick questions like, are you bigger than a bread box? Are you smaller than a skyscraper? And then you increasingly get to a narrower and narrower band of possibilities until you finally give up and say, all right, I think you're here. Let's visualize that game of 20 questions graphically. So on this screen, this blue line represents the actual position of, let's say, the x-axis of the right joystick. Think of this as the voltage level that it's outputting. So we can represent the minimum amount of voltage as, say, a value of 0, and that would be just 1 dot. And it can go all the way up to, say, 63, which is hex 3F, which is up here. So let's run through this algorithm when we start at around, let's say, hex 14. The first thing we do is we take a guess and we ask, well, are you here? So down here you can see the approximation that we're trying to guess. Is it at hex 20? And the comparator returns a low. The reason is that the comparator bases everything on what's coming in on the plus side. And that's the side with the joystick. So if the positive side is higher than our guess, it returns a high or a 1. And that 1 comes out in this bit from P of 1. If the joystick instead is lower than our guess, then this returns a low or a 0 on that bit. So since it's a low, we've got to guess less. And this value tells us how far to decrease our previous guess by for our next guess. And you'll see this is going to keep on going down by a power of 2 each time. So our next guess is down here, and we'll guess this, and we'll ask, is the joystick higher or lower? And the answer is it's higher, so we have to guess a little bit higher. So our adjustment here is going to push us forward. We ask again, and now it's lower, so we have to go lower, and so this is going to have us go a bit lower. And so that brings our current approximation of hex 14 right in line with the joystick axis position of hex 14. Let's pause this for a minute to ask, how exactly are we using the comparator? What are we comparing with? What is actually coming in on the negative end of the comparator? The DAC! So this is what I mean when I say that the analog to digital converter contains a digital to analog converter. The truth is there is no dedicated analog to digital converter in hardware. The analog to digital converter is really a set of a few things. It's this hardware comparator, it's this DAC, and it's this software algorithm. So each time we're making a guess, what we're doing is we're sending bits into the DAC so it can produce an analog voltage level. And now we're talking the same language because we have an analog voltage level coming in on plus, we have an analog voltage level coming in on minus, and now we can ask which is bigger, which is smaller. Then our algorithm will change our guess each time, going up or down by half as much as it went up or down last time until it slowly narrows in on the real voltage. If this is sounding or looking like binary search to you, that's because it's very similar, but it is not the same. Back to our example, we've got a perfect guess. If this was binary search, we would be done. But there's an interesting limitation with the comparator. The comparator is capable of sending out a 0 or a 1, a low or a high. What happens if the voltages coming in on minus and plus are exactly equal? What will it do? I don't know. I don't know if anyone knows. Maybe the answer is, it's impossible in the real world for two voltages to ever be exactly the same. There's probably always going to be some slight difference. This is going to have whatever tolerance it has, and it's going to produce whatever answer it produces. It's never going to say yes. It's always going to say too low or too high, too low or too high. So, was this too low or too high? According to my arbitrary visualizer, it's too low. So what are we going to do? It thinks the joystick level is too low, so it's going to guess a little bit lower. And now it realizes, nope, the joystick level is higher than that, so it's going to bump it up. And it's going to ask again. It's still too high. But our adjustment here, which looks like 0 but isn't really 0, isn't going to have any effect. So ultimately, we stick with the inaccurate guess, even though JOYIN got the value perfectly before.
That is so shocking. I'm very surprised.
The reason I say this looks like it's 0 but it isn't really 0 is because this is actually 1/2 in binary. Think of this as a binary 0.1. When we try to add 0.1, nothing's going to happen. It's going to get lopped off. But when we subtract it, there will be an effect, and it will go down. So let's see what happens with a different value. What if the joystick were at hex 15? We're going to get a low, so we go down, We get a high, so we go up. We get a low, so we go down. We get a high, so we go up. We get a low, so we go down. And now we're back at this half, this 0.1 in binary. And the comparator kind of arbitrarily decides the joystick is too low, and so we're going to subtract not 0, but we're going to subtract 0.1. That's going to have a ripple effect through the bits, and we're actually going to go down. We had a perfect match before, but this is going to be the ultimate value that we return. Let's take a closer look at the JOYIN code. This is directly taken from the Unraveled series, but I've renamed some of the labels just to make things a little clearer. The loop where we get closer and closer and closer to the actual value of the joystick is this, what I'm calling this test bit loop. This is an example of a successive approximation algorithm. It's like binary search, but not quite the same. From the visualizer, I use these letters B and A because these are the registers that tend to hold these values. So B is the current best guess as to what the level of the joystick is. A tells us how much to adjust B by, either positive or negative, and that adjustment keeps going down by a half. What did I mean when I said that A goes down to a binary 1/2, a binary 0.1? One of the simplifications that I did in the visualizer is I kind of finessed the issue that the DAC is fed by the upper 6 bits of PA2. So the value of the B register isn't quite what I was showing, it's actually 4 times that. It's that value shifted to the left twice. And similarly, A is also shifted to the left twice from what I showed you. This is the original code. And this is the condition where we know to stop the loop. We stop the loop when A goes down to 1. That means the final iteration of the loop that we completed, just before we did this, had A being 2. That means this was the value of A the last time it was applied, which means we applied this adjustment to B on the final iteration. But the upper 6 bits are up here. We're applying an adjustment where 1 is below those 6 bits that matter. So what if B were this value just before we applied A to it for the last time? If we needed to add A to B, then our new B would be that. And guess what happens? This is the value that we take, and it has not been changed. Adding 1 in this slot makes no difference. However, if we had to subtract this from here, then we would have ended up with this B. Again, this bit does not matter that it changed, but we did end up changing a bit here. So we ended up subtracting from that upper 6 bits of B, the lowest bit. So that's a little bit weird, but it gets much weirder. Let's go up a bit before the successive approximation algorithm starts. We turn off the audio because we're playing with the selector and we don't want any of these bits that we're sending out through the DAC to go to the TV. Fine. X points to those 4 memory locations where the joystick values that we evaluate end up. B tells us which one we're going to play with, so we're going to do 3 first, then 2, then 1, then 0. That's fine. What's going on here? What does this mean? What's going on here? What does this mean? We're going to do something 10 times because we really want to get a stable reading. And if we do it 10 times, then it will be stable. Or so these comments would have us believe. Let's follow this value. We store A and B onto the stack. This is just a synonym for pushing D onto S. We begin our algorithm. We do the algorithm. Hello, algorithm. Thank you for being yourself. When we're done with the loop, we break out. We shift our approximation to the right twice so that it's a suitable value for measuring the joystick between 0 and 63. And then we ask, is this equal to the last try? We really want it to be equal to the last try, because if it is, then we go and save it. We go doot, 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 doot. We save it, we pop that A and B off the stack, and we decrement B so that we'll look at the next axis. And if there's no axis left, then we're done. So we really want a match here. If we don't get a match, then we decrement the A that we stored onto the stack. We decrement our tries that started at 10 and goes down. And we go all the way back up to here, reinitializing and doing the entire successive approximation algorithm again. So we run this 10 times, hoping to get the same value twice in a row, and if we do, then that's great. The only problem is that's wrong. That's not what's happening. The unraveled comments are wrong.
That is so shocking. I'm very surprised.
Let's go back to that compare that tells us if we're done with our tries or if we need to do another try. We compare the result of this attempt with wherever we were going to write it. So remember, when we go to write it, we're going to decrement x and write it there. And so this is that spot we're going to write it in, and we ask, hey, are you the same as what we wrote there last time? Except we did not write it last time. We never write it unless we end the loop and come down here. So we're looping for 10 times, supposedly seeing if the last try equaled the try before, and breaking out, but it won't because we don't write the result of each try. We write the final result after the loop is done, and we do that here. Unraveled is incorrect. And when I saw this, I went to the CoCo Discord and I asked, is there a bug in the ROM? What's going on? Why is it doing this 10 times? It would seem that what we're really comparing with is not the result of the previous try, but the result of the last time someone called JOYIN. Because that's the last time we would have actually written anything to the location we're comparing against. So basically what this is doing is it's trying 10 times to get the same result as the last time JOYIN was called. And if so, we're golden and we break out. But if not, whatever the 10th result was, that's what we're going to write this time. This resulted in a rather lengthy discussion. Thanks to the folks on the Discord, I understand a little better some of the difficulties in trying to read an analog joystick. It can be quite noisy. It can be noisy because mechanically the stick, even though the user isn't moving it, maybe it jitters a little bit and it upsets the potentiometer. Maybe there's thermal noise at the potentiometer. Or maybe there's electromagnetic interference that's changing the voltage. All sorts of reasons could make reading that analog value quite unreliable. So perhaps what's going on here is assuming that this was used by a basic program in some kind of a loop, trying to figure out what the player is doing with their joystick and how to adjust game elements accordingly. It's better to just return the same answer to the joystick if you can't be 100% certain that there really was a real change. So this isn't trying to get a clean read of the joystick right now. It's trying to see if there's really a difference between the joystick now and the last time JOYIN was called. Only if after trying 10 times we were unable to get a match with what it was before, then we'll just return the new value. And by the new value, I mean whatever the 10th trial gave us, that's what we'll return. And finally, one last surprise. Imagine that the signal coming in from the joystick into the comparator is actually not noisy. There is still an issue with getting a clean read of that signal. That issue is that we've got this loop. We're not making one read out of that comparator. We're making up to 6 reads. And each time we do a read, we're sending some new bits onto the minus, and we're getting that same signal from the joystick that we compare each time. But I just lied. We're not getting a same signal from the joystick each time. We're getting whatever that signal is right now. So what if the joystick happened to be moving? The first run through our loop, we're going to be comparing our guess with one read of the joystick. The next time through the loop, we're going to be checking our next guess against yet another version of the joystick position. And then when you add noise back into the picture, this makes it even worse. You don't have to be a superhuman who's moving the joystick at a very fast rate to get different values here. The noise is enough to do it for you. Each time we compare our guess, we're comparing it with a different value.
That is so shocking. I'm very surprised.
Thanks to the discussion on the Discord, I learned about something called a sample and hold circuit. This is an analog circuit which can take a voltage and just hold that voltage value for a while. Apparently you build this up from a capacitor and a transistor. Maybe there are other ways to do it. But without any digital circuitry at all, you can basically store a voltage value so that you can test it multiple times and not see any kind of drift. But there is no sample and hold circuit in the CoCo. So we really are doing these dirty reads one after another, assembling them together into a final guess and hoping it works. Perhaps the true shocking surprise here is that it works at all. Also, as stated on the Discord, one of the saving graces is that 6 bits of resolution isn't that much. And if we tried to do a higher resolution DAC and algorithm, that might just be too much for these circuits to deal with, and we might not really get any decent reads in that case. Well, I'm all out of surprises for today. I hope you found that interesting and informative. I certainly learned a lot myself when doing the research for this video. If you would like to play around with that successive approximation visualizer, you can download it and run it on your CoCo. There's a link to it in the description. Until next time, as always, thank you for watching.